get going. I really wanted this to be an interactive class, sort of, with a bit more attendance. But anyway, I think we have people who are interested, so I think we can get the inputs. So as I mentioned towards the end of last class, we are trying to look at, in terms of whatever you have learned in structures related courses, starting from, let's say, strength of materials all the way to any electives that you have taken, etc., to what you have studied even in this course in the last 18-19 lectures. So what we are trying to do over here is to put everything into a single framework. And before talking about that framework, I just want to get certain inputs from you. I don't know if some of you have looked at the video of the previous session that we had of a similar class. Anybody has taken a look at that? No? Okay, that's good. I actually wanted a little bit of suspense in that, in terms of what we're going to populate that first row with in terms of the headings for this particular table. So we have looked at the modeling of materials and structures, both metals, other conventional materials, as well as composites. And we said that typically, especially for composites, you break it up into three parts: the micromechanics, the mesomechanics, and the macromechanics. We already looked at the micromechanics, where we tried to equivalently homogenize a single layer, which is having fibers and matrix and many other additives in a realistic case. And then we looked at also the assumptions that were involved for the mesomechanics, in terms of how you can analyze eventually a laminate, where you can equivalently homogenize not a single layer but multiple layers. We didn't go exactly into the equations and other things, because, as I said, we are going to do it from a different kind of a paradigm, and that I'm not introducing today, but we will slowly get into that. Probably we have just another 5 or 6 classes. So, but that is sufficient, because I'm not going to introduce to you the whole derivation, as I said, and only the end results and how you can actually utilize it when you go forward for your own duties in terms of applications, and those who are not from a structures background to look at it from a perspective of what is the state of the art in structures. So when your colleagues talk about it, you understand where your inputs are going in and where their outputs are going to come in and be utilized by you. So that's the whole idea of this. So in macromechanics, and as well as the previous two, micro as well as meso, there are certain things that can all fall into this framework. It's not a very rigid framework, but it helps us to kind of understand. It's more of let's say a pedagogic tool, so that you can whenever you are concerned about a new topic to be something totally new, you can try to see if it fits into this structure, so that you will be able to understand things a little easier. It has helped me, and it has helped a lot of students in the past, many of who are professors in IITs and many other institutions around the world, and even today they continue to use this particular pedagogic tool in their own teachings as well, and they say that not only they benefited from it, but the students that they are teaching are also benefiting from it. It's not a whole lot. It's because once you know it, it looks like it's obvious and it's nothing new. But just that putting it in words and putting it in a particular pictorial form helps us create that kind of mnemonic for us to keep things much simpler than what they are. Because it's not just structures or solid mechanics, but most subjects, half the subject is learned once the terminology is learned. Because it's the same basic math and physics that we learned in high school that we are trying to apply, just that we use certain jargon which is associated with that particular career stream or that particular industry, and therefore it gets kind of specialized in a particular way. So once you understand the terms and what aspects of the math and physics that we already know it borrows, then things become much simpler. So the first of such things in math are variables. So essentially you deal with certain quantities which can change with certain independent variables. They could be space, they could be time, and when they change, certain things you know how they change already a priori because you're probably, let's say, measuring, or if it's a design problem, that's your intended kind of behavior eventually. And there are certain things which you don't know, which is what you are there for, to find out in terms of those known quantities, what are the unknown quantities, so you want to determine them. So this connection between them is essentially in terms of equations. So these are the three things. First, you have a set of knowns and unknowns, then you have a set of equations, and those equations in turn depend on certain parameters and what kind of parameters they depend upon. All of that, these questions we will try to answer and fit it into this particular table. It can never be a comprehensive table, just that it's based on the inputs that I'm going to get from you, based on your own, as I said, subjects, the exams that you have done, assignments that you have done, not just in this course but related to structures and solid mechanics and strength of materials, also GATE exam that many of you would have appeared for. What typical questions are asked related to structures? What are the quantities which are given to you in terms of known quantities? What are the quantities which are asked from you in terms of the unknown quantities? That we will look at first. So later on, we will try to look at what are the equations that are required in order to solve for them. We will go to that in the next step. And then we will also look into what those equations eventually depend upon, because it's not just variables, right? In math, you also have constants. So these constants typically help us within the equation to help determine the unknowns in terms of the knowns. So we will go step by step in that. And as always, I found it very useful to ask questions and then try to learn from that. So the first question that we will ask is in terms of what I was just describing, what are the variables that would help describe the state of a mechanically loaded structure, because the otherwise can get too big and too much to for this, even this large board, that blackboard that we have. So we will try to look at some of these variables and different types of questions. What is unknown in one question can become an unknown in another question. So we are not bothered about whether they are known or unknown. We just bother about the variables, some irrespective of whether they are known or unknown. So what are the variables which help us to determine the state of a structure? Let's say we have a structure like this. It could be a beam, it could be a plate-like structure, it could be a brick, a 3D-like structure. But whatever it is, there are certain variables which are known, which are unknown. So can you start naming them so that we'll try to populate this? I might make mistakes. We can always come and correct that in terms of where it fits in. There are certain variables which could probably fit in multiple columns as well. So as I already mentioned, there's nothing rigid and fast about this. So let's start doing that. So go ahead, and any one of you keep on naming variables, and I'll try to put them in various columns here. Stress, okay.
Geometry, parameters.
Some examples of geometric parameters.
Thickness.
Okay.
Area, moment of inertia. And the length also. In case where.
Okay. What's that?
Length. I mean.
Length. Yeah. Sure. Sure. Yeah. Yeah. What else?
Material properties.
Material properties. Material properties. A few examples of that. Okay. Since we're dealing with composites, we will qualify that by writing subscripts just like we do for the moment of inertia. Yeah, anything else? Yeah. So in this course itself, we will look at quite a few of them. Else? Density. Density. So mass density per unit volume. What else?
Shear model.
Yeah. G.
So where applicable for materials which are ductile, so we could probably have that as well. What else?
In case they are not operating in elastic range, then the stress strain relationship also. But
Sure. So this could be a nonlinear function of gamma Ij.
External load.
Okay. Yeah. Some examples of typical loads.
force,
Distributed.
Okay, force. Typically a vector, so components in 3 different directions depending upon the coordinate system that you introduce. Yeah. Torsion. Torque. So we typically refer to that as one particular component of the moment, just like the forces, you could have 3 components, you could have one particular component there. So let me generalize that to mi. Okay. What are the other kinds of moments other than the torques? Bending. So including bending moment. What else?
pressure.
Pressure.
Cyclic loading.
Cyclic loading. So what kind of differences would that lead to a cyclic loading as opposed to a static loading? What are the other features that you have to probably need in, let's say, material properties or geometric properties to deal with that?
Asymmetrical.
Yes.
Boundary condition.
Boundary conditions, yeah. Can you qualify that a little more? There are 2 types of broad categories of boundary conditions, right? So you have what are known as, in mathematicians parlance, you would call it as Dirichlet or Neumann. But let's keep things simpler here, natural and geometric boundary conditions, right? So typically, for example, in a beam, let's say it's cantilever, you have the fixed end, you are talking about the geometry boundary conditions there. In other words, the displacement is 0 and the slope is 0, right? Whereas at the free end, you're talking about the loads. So it could be either an unloaded thing, in which case all the forces and moments are 0, or you could be applying certain tip forces in different directions, or tip moments in different conditions. Could be torques, could be bending moment, could be all of them. Okay. So, or even if you have this is just an example of a beam, but any 3D structure also, you would have the boundary of that structure, and you would be at certain areas, certain parts of the boundary, you would be applying boundary conditions which are in terms of the slopes and displacements, essentially geometric boundary conditions, and certain other places where you are applying the load boundary condition, where you know what is the load that is being applied, right? So let me put them separately. So just putting a tilde to mention that they are on the boundary, they're not something in the interior of the structure. Okay. There could be structures which have an interior boundary also, so it could have a multiple boundary problem. So for example, a sphere or a pressure vessel which has an outer surface and inner surface. So the inner surface is also taken into account over there. So the other type is so you could be talking about, let's say, some displacements in the different directions or some slopes in the different directions, right? So you could be referring to that. Depends on the specific problem, how you're going to frame it from a mathematical perspective. If they are more in terms of the unknown quantity itself, then it essentially falls over here. If you're talking of a displacement-based formulation, There are also certain things which are force-based formulations where everything will be derived in terms of force. The displacements will be substituted in terms of force and obtained. So it could interchange over there. But the classical conventional way of doing it is to solve everything in terms of displacement and eventually get back the other quantities. So we will keep this separately like this as the boundary conditions, the input that you get. Anything else?
Secant thermal coefficient of thermal expansion.
Coefficient. So once again, because we're talking of anisotropic materials, we will put an alpha I associated with that. So it could have different coefficients of expansion, different directions. For a unit increase in temperature, let's say per degree centigrade or per Kelvin, how much of expansion you're going to have with respect to the original length is what we are talking about here as alpha I. Yes?
And temperature in the rooms for the appropriate or heat flux.
So even though I'm talking of mechanically loaded structures, we will take those as well because they are also quite common, the temperature, etc. So, and so it's more in terms of rather than the actual temperature, which is important for, let's say, creep, etc. There's also something which is even more important is in terms of the change in temperature with respect to time, how it is changing, right? So that can cause certain problems, yeah. So the material property associated with that is alpha I. Anything else?
So in the geometric parameters, the shape of the structure, I mean the exact dimensions.
Correct, right. So yeah, other than your length and thickness, etc., the actual shape that you're talking about, because only after you define the shape, then you're talking about the sizing in the different directions, and the sizing is what we already took into account. Let's say the thickness, the length, let's say the breadth also, etc. So that's in a cuboidal structure. But for example, if the shape is circular, then you're talking of the radius and many other things like that, right? So let's say, yeah.
Deformation and strain.
Come again?
Strain and deformation.
Strain and deformation, very good. Okay. So again, strains, there's so many different classifications that you can have, right? For all types of strains you're familiar with.
Shear strain.
Okay.
Longitudinal elastic.
What is that? Launched?
Longitudinal strain.
Yes, yes.
Transverse and long.
Elastic and plastic strain.
Okay. So the limits for that, of course, will be given by something like this, so that you separate those out. So the reason why I'm mentioning in the context of certain things is that there are related parameters in multiple columns. It's not that it's just fixed to one. For example, when somebody mentioned cyclic loading or fatigue, for example, you mentioned S and curve. So they are falling in different, but they are kind of related for a similar kind of a problem. So think of all kinds of exercises that you have solved, preparing for GATE, the exams that you have done. What are all typically the known quantities which are given to you? What are the unknown quantities asked of you?
History of stress also.
History of stress, very good. So sigma as a function of time, right? Apart from being a function of the spatial coordinates. Same thing with this one. So those are independent variables that we are dealing with, xi and t.
Type of joints.
Type of joints, very good. Yeah. So again, the joint, depending upon what kind of joint it is, it is typically a boundary condition between two parts of the same component. So we can put it in both of these. So you classify different types of strains. So similarly, like shear, normal, elastic, plastic, you could have here as well, right? Like that, can you think of the classifications of deformation? What all types of deformation you're aware of?
Volumetric change
Okay,
in shape
very
and
good.
change in size.
Let's say delta B, change in volume,
Change in angle.
change in angle, okay. Change in theta.
Change in individual dimensions without
Okay.
change in angle.
We also use this. Individual dimensions, we call it as delta UI. UI itself, let's say. So for example, if you have a cuboidal structure with a Cartesian coordinate system where you have talked about the length, breadth and thickness, the change in length, the change in breadth and the change in thickness would correspondingly be U1, U2 and U3. Okay? So you have displacements, you have rotations, so you can also move the delta over here, let's call that as the actual change. So what else?
Deformation rates.
Huh?
Deformation rates. also.
Deformation rates, okay, very good. So you could have UI dot, theta I dot, and delta V dot, say, change in volume.
Viscous dissipation and the material properties.
Viscous dissipation. Yeah.
Viscous.
Strain energy density, okay. We introduced that as one of the assumptions. Its existence helped us to claim the major symmetry of the stiffness matrix and the compliance matrix as well, right?
Traction.
Traction, okay.
So stress concentration factor.
Coming in?
Stress concentration factor.
Okay.
Should something whether geometry, I am confused.
Yeah, yeah.
Geometry
So-
or geometry.
Maybe combination of both.
Like notching effect.
Correct,
Depending on
correct,
the shapes
correct.
and so on.
So that's a very classic example of certain things which are having both kinds of characteristics or properties, right? So you can put it as the stress concentration factor over here, as well as based on what kind of geometries are associated with it, as you mentioned, notch or a crack and many other things, right? Yeah.
Critical buckling load.
Critical buckling load, okay. So once again, see the critical buckling load, for example, simplest case you have is the column, which is simply supported, E is pi squared EI by L squared, right? So it has certain properties which are associated with the material, it has certain properties which are associated with the geometry as well. So there are certain things that we need to, because these are compound quantities, these are not quantities which are individual, so they are dependent on other quantities, and so we can put it on this as well. The I part of it, the moment of inertia comes from there, the E part comes from there, the L also comes from here, right?
K1C.
The boundary condition also in that case, they are simply supported, etc. That's also going to be done. Yes.
K1C.
KMC. So,
What is Q?
so it's the first mode. You have the stress intensity factors. So you were talking about, we didn't list that separately, right? So it's essentially a fracture mechanics concept that you have. So it is a material property which determines how the fracture will grow in a particular way. So similarly, you could have the other modes, and you could have something called a mixed mode and things like that, right?
The triaxiality.
Okay. Stress triaxiality, exactly what you mean?
So like especially when there is loading in multiple directions, because of interaction between multiple directions, the von Mises stresses and all the definition will change. So the material behavior will change based on how the loading is.
Correct.
So
So typically you're talking about the potential of failure in multi-dimensional loading kind of a situation, right? So you could also think of it as, let's say, failure envelope. So if you're loading it in just one direction, what he's saying is that there will be a certain value of stress at which it would yield or it would fail ultimately. But if you're loading it at the simultaneously in two different directions, let's say you're pulling it this way as well as this way, then it could fail at a stress value which is smaller than the failures in each one of those individual directions. Instead of a unidirectional load, you're having a bidirectional load. So he's talking about triaxiality, where you could have all three directions, and maybe you could even have shear, etc. So when you have all of those, when typically it will fail, that is determined by what are known as failure envelopes, where you can plot, let's say if it's just two stresses that you're applying, let's say sigma xx along the length, sigma yy along the width, then you plot sigma xx versus sigma yy, you get a closed curve which says that if your stress state is anywhere inside of that, so you're plotting sigma xx versus sigma yy. If it's inside that envelope, then it doesn't fail. If it's on the envelope, it does just fail. If it's outside the envelope, it's already failed. So it's more of a theoretical state that you're talking about. So that's just bidirectional. He's talking about triaxiality, where you could have a failure envelope which is more like a balloon now, a volume, and once again the same condition remains in terms of if you are on the boundary, failure has just occurred. And each of these will typically intersect those axes on the sigma u's of those particular directions. Sigma u1, sigma u2, and sigma u3. But in between, it would be at smaller values compared to both of them. Yeah. Triaxiality, anything else?
shock factor.
Shock factor. So can you explain that also?
Basically, if a load is applied in a very short duration,
Yeah.
then the load behaves as if it's a much larger load applied on a structure.
Sure. So typically we call it as an impulse, where you're plotting the force versus the time and looking at the area of that, and you're in the limit as delta t tends to 0, duration over which you're applying the force, and your f actually goes to infinity, but f times t is what we are talking about as the impulse, right? So it's one type of loading. It's typically in impacts. So let's call it as impulse or shock loading. Anything else?
So the stiffness of the component which will define its frequency in case the loading is cyclic.
Very good, yeah. So we say the natural frequencies omega n, where n refers to the mode in which that natural frequency is. It could be a bending mode, it could be a torsional mode, it could be an axial load mode, etc. So and also in each one of them there could be a first mode, second mode, etc. So we're talking of all of those over there.
having geometry and material together.
Yes, it will. Yeah, it will have certain. Very good. Again, it depends on what level you're talking of. The examples that I gave of bending, etc., there you will have the geometric influence. But if you're talking of just, let's say, for example, a spring mass system, you're essentially talking of square root of k by m for that, which is essentially two material properties, mass coming from the density. But again, yeah, the mass, depending upon the volume of the structure, can come from that as well. So it's right. In general, you can put it at both, especially when you're talking of beams and plates, which is what is more of concern for flight vehicle structures.
Material toughness, hardness.
Very good. I'm running out of space. Can you think of certain variables which are associated with the columns that are not populated? I have not yet told you what those columns are, but I think you would have guessed by now in terms of the kind of quantities that they are putting in each one of them. So let's say take this column for example. Anything else related to strains? Yeah, we talked about displacement rate like that. You could have the strain rate as well, right? Did we already put that? No. It's typically a very important thing there in terms of what you talked about, as well as higher frequency vibration problems as well, where the material properties can also get affected by what gamma ij are. So in other words, your sigma uij, for example, could be a function of gamma dot ij. It may not be a single particular material property. It can start depending upon that. High strain rates and low strain rate failure limits could be different. Temperature gradient, I think we already put that somewhere, right? Yes.
Accelerations, like in a free body.
Yeah. Let me just also maybe it's not just the change in temperature, but the gradient that he's talking about, which could be written in terms of a gradient of T rather than. Sorry, I missed yours.
Acceleration,
Okay.
inertial acceleration.
Inertial accelerations, okay. So the acceleration.
Loading.
Should be dynamics. Yeah. So in terms of the inertial force, it is that it also involves the mass as well. So if it's the acceleration, which is an angular acceleration also that is associated, which could involve the moments of inertia, products of inertia, etc. So certain material properties can also come into picture. Yeah.
So temperature gradient
Yeah,
is like
one more thing, I'll just finish that. Yeah, so acceleration is also the change in the geometry with respect to time. Essentially, it could be acceleration of the entire body as a whole and points within the body moving relative to each other. So there is a certain acceleration which is associated with that, which we have already put in terms of your u dots and theta dots. You can also include the acceleration here as ui double dot and theta I double dot. So this I would rather call it as the inertial force. You are mentioning something, Rajesh?
So temperature gradient is kind of strain, right? Like it's a gradient over the space. So
Uh-huh.
temperature gradient.
Yeah.
Like, is it under this gradient?
Yes, you're right.
Strains, not geometry.
Oops. Yeah, but it's the quantity, how it is changing with respect to the independent variable change can be there in other cases also, but what we are talking about is the numerator. So the temperature is essentially like a load that you're applying. So how it changes is also a load. So for example, if delta T in a particular direction is more or less, it's more in terms of how severely you're loading the structure. So I would say it's more better fit over there, even though I see your point that it's a derivative with respect to spatial coordinate, and that's why you're talking about that. But it's more of a loading.
So, but if you put gravity in deformation, then heat flux and conductivity.
Correct. Right.
That has to also.
True. Well, conductivity is more like a material property, so it would probably put over here, right? So conductivity in many different directions. Yeah. The heat flux is essentially yeah. So maybe I will just remove it from there to avoid confusion.
So discontinuities within the object under load.
Discontinuities within the object. So the discontinuity can typically be in terms of so because you typically will give the discontinuity in terms of the boundary conditions. So for example, if it's let's say delamination that has occurred, so essentially it's a free edge now. In other words, a free surface, sorry, not a free edge, but a free surface that has been created. So free surface means that you're essentially talking about the loads over there. So I would rather put it over here. Because after the discontinuity, what happens is also important. Certain between two lamina, there could be a delamination, but it could be touching each other. So it could have already separated. In other words, it's just a contact mechanics that is taking place, in which case it's more of a load over there, or it can be a free edge. So I would rather not put it over here. Even though in terms of defining the discontinuity itself, how large is the delamination, where exactly it has occurred, etc. So that could come in. So I could write it as rather the discontinuity geometry. Not just the delamination, but let's say is a matrix crack. Where exactly is the matrix crack? How large is it? So all of that is again in terms of the geometry of the discontinuity.
So then grain boundaries will come along with that fracture.
Yeah.
Traction separation is what we are going for delamination.
Correct. Very good. Yeah.
Centrifugal force.
Very good. Yeah.
So way of manufacturing something, like density will be almost similar in forged block or casted.
Correct. Right. So the material properties could all vary as a function of the manufacturing process. So I think that it is. It's more of the impact of that manufacturing process. And during the manufacturing process, not only the properties change, but also you're typically applying certain loads also, which could be, let's say, a pre-stress or something like that. So that could also be happening, which you could probably look into this. Let's say manufacturing induced. It's more like a load that is coming over there, right? To take that a little further, after manufacturing it is transported, so transportation loads could be there. again, maintenance and the person who are handling it. So typically you could have handling loads as well.
Room stresses. Second question.
Yeah, very good. Yeah. Okay. So essentially you're talking of, instead of a sigma ij in a Cartesian coordinate system, you're talking of a sigma in an r theta kind of a coordinate system that we are talking of. So where you're essentially talking of sigma theta theta, right?
Crystalline material.
Very good, yeah, yeah. So it's the microstructure, let's put it in a more generic sense. For metals, for example, you could have a crystalline structure. For polymers, you could have a polymer chain, etc. So essentially the microstructure, so all of that can dictate all of these. So just like the manufacturing processes can dictate your, let's say, microstructure, can also affect it, and they're related sometimes. The manufacturing process can alter the microstructure, including the crystallinity, and that can result in changing the properties. Yes.
Surface finish.
Surface finish, okay. Where do you suggest that? Because one is in terms of the geometry of the finish, the other is in terms of the properties
Boundary condition.
as well. Yeah,
Boundary
yeah,
condition.
yeah. I think that would be more appropriate. I think it would be more in terms of a geometric boundary condition, right? I think that is probably the most appropriate place for it in terms of the surface finish. Because, for example, if it's the wing, the cover skin that you're talking about, how the flow stresses could be, especially the viscous part of it, and how it impacts the drag, etc., could depend on that. So essentially, it's something which is associated with the boundary.
The material distribution, which will lead to load flow.
Very good, yeah, yeah, yeah. So you typically have not just single material, but many different materials making up sometimes even a component or larger structure like a wing, etc. So the material distribution becomes important as well. So, yeah.
Material compatibility.
Yeah, the compatibility between them. Once again, we can think of it in terms of both the geometric and the natural boundary conditions that are happening between them. For example, the compatibility between a fiber and the matrix is essentially, we're talking about the interface between the fiber and the matrix, what kind of physical processes can take place, but if it's, let's say, a chemical reaction, etc., something that is associated with the specific type of material as well, so it could fall into this as well.
So operating environment has to take corrosion.
Right, right. So just like you have thermal environments, you could have the corrosive environments. Okay, both chemical as well as electrochemical corrosions. Yeah. Anything else?
So aspects like stress corrosion, cracking, they come into.
Correct, correct, yeah, yeah. So they're kind of related. So this is essentially the environment, how it is impacting on it, and the environment in turn can so either be thought of as a load or as a change in the material property itself because of that over a sustained period of time, typically, right? For example, humidity can change some of these properties if it's subjected to humidity for a long period of time. Creep, we already mentioned, where subjected to a particular temperature for a static load for a long period of time, things like that, right? Yeah. So some things that you're giving are also valid, but I'm just not putting because some of these are getting too crowded. Yeah.
Stress and strain may have different definitions also. Like.
Very good, very good. Yeah. So like the example that we talked about in the class are here. So different types of stresses, different types of strains. So that's in terms of the very definition itself. Within each one of them, you will have these categories as well, shear and normal that we talked about in both cases. So I think we'd probably stop with this. This is good enough. So which variables describe the state of a mechanically loaded structure? However long we continue this class and how many a few more people are there giving their inputs also, this can never be a comprehensive thing. There will be so many other things that can always keep coming in. We just wanted to get a rough idea of where we stand in terms of this. So the next question which we shall ask is in terms of, can we classify all of these listed variables into 4 general categories? You would be surprised because I have put more than 4 columns over here, 7 specifically over here. But I'm asking about specifically the variables. But we have not only put variables over here, we put certain material constants as well, certain conditions as well over here. Similarly, in terms of boundary conditions, geometric boundary conditions, etc. Those are all not actual answers to my question, first question, which was which variables describe the mechanically loaded state. And again, we also talked about other types of loading other than mechanical as well. So that is also there. But if you look at purely the variables which define the particular state of the structure, as the load progresses with time, the state can change, and therefore it has to be redefined in terms of those quantities. So if you look at that, it's essentially the odd numbered columns over here, which we will now give them the titles, generalized loads that we are talking about, and the generalized stress that we are talking about, and the generalized strain. And the generalized deformation. You're saying generalized in the sense that if I say a force, it also could include moments. If I say, let's say deformation, it could also include rotations and things like that. So we are generally talking about all kinds of quantities which are associated with that. We are clubbing into these 4 categories, and more often than not, you would see that most of the variables which are regularly used in all of these courses, strength of materials, all the way up to this particular course, or even more advanced electives that you eventually take, most of them would fit into one of these columns, these 4 columns that we have talked about, the loads, stresses, strains, and the deformation. There could be a few which are more advanced concepts or topics which could be a little hazy. You might want to, because they might have certain aspects which are both of 2 different kinds that you're talking about. Now, if you look at this overall thing, typically when you're looking at it from a more straightforward manner in terms of how a human being typically perceives with his or her sense organs, you're typically more attuned with the loads and the deformation. And in terms of this being, let's say a cause, and this being an effect. So, but typically what happens is if you're trying to directly relate these load to the deformation, the equations and the mathematical model involved are much more complicated. So you introduce these two in-between quantities. Not that these are not straightforward, but I'm talking in a relative manner in the sense that these are a little more abstract quantities. So because you're talking of something that is associated in terms of a certain intensity that is associated with the load, and you're talking of a certain intensity that is associated with the deformation in terms of, let's say, deformation gradients and things like that. Here again, you're talking of certain gradients associated with the load in terms of aerial gradients, etc. We're talking about that. We'll go into the specific details of that later, but let's just see what the other three columns are, which we have not yet talked about, because we only talked about the variables which are defining the state of a certain loaded structure. So if I have loaded it in a certain way, either I can give you the load and ask you for the deformation, or I could say I need a certain level of deformation in this particular case. What is the load that I need to apply in order to achieve that kind of a deformation? So that load could be not just a single type of load like one particular direction force, but could be a combination of forces and moments and distributed and concentrated, etc. at different locations in terms of their distribution spatially, and also with respect to time. At different times some loads can come in, sometimes loads can go off, or they can vary continuously with respect to time, etc. But essentially either the load becomes the cause and the deformation becomes the effect, or vice versa in terms of a design problem where you're looking at a particular effect and you're trying to determine the cost for that. So these can be interchangeably used. But many a times, this is something that you observe in life also. Why did this happen to me? Even whether a good thing or a bad thing, you typically say, why the hell did this happen to me? Because there are certain things that you would have probably done and you would have forgotten. So it's what we call as the law of karma. So essentially that is the cause-effect relationship, Newton's third law. Every action has an equal and opposite reaction. Just that there could be a time spacing between them. There could be various aspects in terms of the complexity. So we cannot understand. Same way in structures also, the direct relationship between the cause and the effect, that is the load and the deformation, is quite complicated. So that's the reason why we introduce these two quantities, the abstract quantities of, relatively speaking, abstract quantities of stress and strain, so that we can go in steps in terms of directly jumping from the cause to the load. Can I go from the load to the stress? Similarly, can I go from the deformation to the strain? And then these two quantities can then relate in some particular way. Because this particular way of looking at it will also tell you what are the quantities on which those relationships are going to be established on. The load stress relationship, what are the features on which it is dependent on. The stress strain relationship, what are the features that it is dependent upon. The strain deformation relationship, what are the features that it is dependent upon. So let's go into the next question over here. We have seen that we can put all these different variables in different columns. We form, what do I do? I just,
the body
will go away, right? So,
can cancel.
Thanks. Yeah. So first we listed out the variables, then we at the time of listing itself I put it into 4 columns, and you could already see where it was heading towards, so which means that 4 general categories or sets that we brought about. Now it's very clear that if I want to connect them, I need 3 sets of equations, because we have 4 sets of quantities. I want to go in steps. This is the first connection that I want to have, the second connection that I want to have, and the third connection that I want to have. And all of those are, in a mathematical model sense, going to be certain equations. So we can broadly classify them as 3 sets of equations which relate these 4 sets of state variables. We're calling them as state variables because they define the mechanical state of loading of that particular structure. So those 4 sets of variables we want to relate to each other, because typically we will know some of these quantities, we will not know certain quantities, and we might be interested in determining those unknown quantities, and we have to take advantage of those equations in order to solve for the unknowns in terms of the node. So that is the direction which we are heading. So what do you typically call this particular equation which you relate the load to the stress? You are applying certain loads and it's causing certain stresses. So the relationship between the load and the stress, how do you determine? Force balance, very good. Yeah, or conservation of angular momentum or conservation of the translational momentum. In general, to keep things simple, we just call it as equilibrium equations. Okay. So the equilibrium, if you look at even the examples that we wrote, for example, the natural boundary conditions, it's saying what is the force and the moment at a particular location. Essentially, it's the load that I'm applying at that particular boundary, what is the force that is occurring, and because of which, what is it creating over there. So a natural boundary condition is just an example of that equilibrium equation, but you probably remember from your strength of materials certain derivatives of the stress related to the body force per unit volume, etc. So those are the main equilibrium equations governing within the structure, any material point inside. On the boundary, whatever is there, that is your natural boundary condition, but essentially they are playing the same role as you mentioned, force balance. So that force balance that is happening can also be thought of more in terms of a law as the law of conservation of momentum, both translational as well as the angular or rotational momentum that is essentially getting conserved over there. Right. Now let's come to this relationship, stress strain, that you're very familiar with. Constitutive law. So we already spent quite some time on this when we introduced the assumptions. Yeah. So that's the constitutive law. And then finally you come to the strain deformation relationship. It could not only involve the deformations, but also how they change with respect to space, how they change with respect to time, etc. So all those things are involved over there. So another example of a strain kind of a quantity is actually your velocities of the individual material points, right? So individual material points, so is essentially your UI, how it is changing with respect to time. So you're talking of a UI dot, UI double dot, etc. Right? So you can actually look at putting all of these in terms of the change with respect to time, rather than here over here. Even though they are quantities which are associated with the displacement, but it's not the displacement itself, it's not the deformation itself, but just like we talked about for strain definition, a deformation gradient tensor in terms of which we can define, let's say, a Green-Lagrange strain, etc. Similarly, the velocities can be defined as instead of spatial derivatives, temporal derivatives, that is derivatives with respect to time instead of with respect to the Cartesian spatial coordinates or the circular, cylindrical or spherical or any curvilinear coordinate system as well. But essentially how they are changing with respect to the independent variables which are both space and time. So that's that particular relationship. So what do you typically call this kind of a strain deformation, where you are essentially dealing with derivatives both with respect to xi and with respect to time. Very good. Okay, so that kind of answers this particular question, the third question that we have asked in the slide, which is which of these three sets of equations, which three sets of equations are relating to four sets of variables that we already found, that is load, stress, strain and deformation, are related by your equilibrium equations, your constitutive law and your kinematics. So those are the three equations that we are interested in. Next thing that we would be interested in is what these connecting equations actually depend upon. We've talked about examples of those already through this whole process, but we'll try to state that in a little more formal sense. So the last question that we're going to ask in this particular slide is, what do these equations depend on for their form and parameters? So you have an equilibrium equation. I give you an example of, let's say, sigma I j comma j equal to the body force per unit volume, which is Fi, let's say. Then similarly like that, all those equations that we have, whether it is the constitutive law or the kinematics also, there are certain quantities that it depends upon. Already you know, for example, the constitutive law which relates the stress and the strain consists of a matrix C, which in turn consists of all these engineering properties like Gij, Eij, nu ij, etc. So we in fact wrote in terms of those as well. But all of those, for example, in the constitutive law, are dependent only on the material, right? So in the purest form, of course, there could be more derivative forms when you go to, let's say, a beam problem or a shell problem. But now, right now, let's say we're talking about just a three-dimensional model for the whole structure or the material. In that sense, in a three-dimensional state of stress versus three-dimensional state of strain is typically dependent on the material properties that are associated with it, because stress and strain are at a given point, and at that point what material you have, what is the behavior of that material under those kinds of environmental conditions that it is in, that determines the constitutive law. So it's more of a material property that this particular column of equations typically depends upon. Whereas the equilibrium equations, for example, is just a law. It's a law of conservation of momentum, for example, we're talking about. It's more coming from the very physics of the problem. What are the natural laws associated with that aspect of physics that are there? So that is essentially leading to your equilibrium equations. On the other hand, if you come to the kinematics, it's essentially things that are changing, namely the deformation, how it is changing with respect to space and time. Okay, so the spatio-temporal variations of that that we are talking about, and there's a lot of geometry that comes into play over there, because how the geometry evolves with respect to space, how the geometry evolves with respect to time. That is essentially what we are talking about in kinematics. So this is mostly dominated by material properties. This is mostly dominated by geometric properties, and by geometry we mean it's with respect to both the independent variables, space and time, and this is typically dominated by your natural laws. So this way of segregation helps us to check out the validity of our models also when we are changing certain aspects of the model. Let's say I'm flying a particular aircraft and I decide that certain components which I'm using metals for, now I want to change with composites. Do I need to worry about changing the kinematics? No, because it's geometry dependent. Do I need to worry about changing the equilibrium equations? No, I'm still flying in the same universe where the same natural laws are valid, so I don't need to be worried about. I'm changing only the metal to the composite, so it's only the constitutive law that changes. Now this could sound like a very straightforward, simple, obvious example, but as you go to more and more advanced topics, you will see that having this kind of a overall framework of 4 sets of variables and 3 sets of equations governing them, and the quantities that they or the paradigms that they depend upon, namely the natural laws, the material properties, and the geometry and its evolution with respect to space-time, then you start recognizing the power of this particular simple classification that we have. May not always be rigorous, it might have certain haziness to it. As we saw, even we were getting confused with certain inputs that we were getting, where exactly to put in terms of the columns. Some of them we put it even in multiple columns, etc. But more or less, you will see that this particular association helps us when we change the geometry features, for example. We need to be more focused on the strain displacement or strain deformation relationships to see how they are going to affect. Overall, if the total mathematical model will get affected, because we are interested in the cause effect. So we are interested in how to relate the loads with respect to the deformation. We said that it's complex because the load, if you're trying to directly relate the load with respect with the deformation, you need to be worried about the natural laws, you need to be worried about the material properties, you need to be worried about the geometric evolution. But now, because you're going in steps, you need to, at each step, you need to be worried about only a certain kind of the relationship, which purely natural laws or purely material properties or purely geometric properties, more or less. But as I already said, this kind of a clear distinction is typically more valid in a three-dimensional model, in a three-dimensional spatial model that we're talking about. But as we go in flight vehicle structures, we will see that we are talking about a plate model or a shell model, we're talking of a beam model, etc. Then we are doing a dimensional reduction, and which involves a certain integration. For example, if I want to model this as a beam, I will be reducing the cross-sectional area, which is a finite area, to a point which is of zero area. What I'm essentially doing there is lumping. So I'm lumping all of those properties in the entire cross-section of all the material properties, all the geometric properties, everything I'm lumping in. So there is some kind of an integration which is happening between the geometry and the material, which you can see in some simple examples that you are probably already aware of, like what is the axial stiffness of a rod? We typically say EA in an isotropic material. That is Young's modulus times the cross-sectional area. In other words, it involves a material property, it involves a geometric property. Same, let's go for a rod. Let me talk of what is in classic textbooks called a beam, which is pure bending, let's say. So when I'm applying a pure bending, the quantity which affects is the bending stiffness or flexural rigidity, what we call as EI. So once again, E is a material property, I is a geometric property. It's the second moment of inertia, pure geometric property. Similarly, when I talk about this being a shaft, let us say, and I'm applying a torque. So what happens is, what I'm interested in is the torsional rigidity, typically GJ that we are talking about. Once again, G is a material property, J is essentially a geometric property. So when we are moving away from a 3D to dimensionally reduced models of plates or shells on one hand, or beams on, which is a generalized sense I'm talking about, beams on the other hand, what we are arriving at is there could be integrations taking place over smaller dimensions, in this case over the thickness, in this case over the cross section, and therefore material properties and geometric properties can get combined into different kinds of terms. So now, the reason why I'm mentioning these simpler examples of EA, EI, GJ, etc., these are things that you have been exposed to already in strength of materials, but even the more rigorous mathematical models, etc., essentially have that characteristic within them, just that the expressions could be a little more involved because you want a little more accuracy compared to the simpler models that you have, but essentially it will have certain contributions from the material property and the geometric property, and that you will see. The other thing is that many times, even though we say this is the where geometry comes into picture, sometimes you will see that the equilibrium equations bring in the geometry as well. Why? Because we are talking of different kinds of quantities over here. If you are talking of, let's say, pressure, and I'm relating to the stress, maybe the geometry may not come into picture. But if I'm relating a force to the stress, obviously the area comes into picture over there. So because we're dealing with certain different kinds of quantities, not only pressures, but also the forces and the moments, etc., that we are applying. So there is an indirect way in which the geometry comes in. But the equilibrium equations by themselves are essentially natural laws of conservation of momentum, for example. So it's only because we are trying to relate different types of entities, not stress to stress, but you're relating like apples to oranges, so you have to bring in a certain conversion which is associated with that. And therefore you would see sometimes the area, the moment of inertia, the torsional constant, etc., actually coming through this path rather than this particular path. So this is the distinction that I want you to remember. This clear-cut distinction is more valid in a three-dimensional model, but mostly in flight vehicle structures we are dealing not with 3D models but 2D or 1D models, and there could be all this a little bit of things coming together. It's more like a mixture that you have of different things that are, it's like a khichdi that essentially results in. So you should be a little aware of that, what is happening. But you can see that in the very flow of that process, which is why we take some three or four simple examples of the same thing. But before we do that, we will just summarize what we have talked about over here. And the examples would be not from the more advanced theories that I'm going to eventually give you the results for towards the last 3 or 4 classes of this course, but more from the point of view of what you already know. So then you will see where those advanced results will actually fit in terms of your own understanding of the simpler models. And those simpler models are things that I already talked about just now: EA, EI, GJ. So these 3 examples that we will see and how exactly they came, we will just revise that without going into the details of the derivation. It's all there in your textbook. For those of you who have forgotten a little bit of that, you can go ahead and revise that. But we will essentially talk about it purely from this point of view. We will start with a structure in which we will apply certain loads. So we will identify what loads are there. For example, in the rod, it will be an axial force. Then we will go to the what is the stress, main stress that is occurring because of that, which is a sigma 11. Let's say if F1 is applied, then sigma 11 is the main stress which is incited, and the main strain which is incited is gamma 11, and the main deformation is a U1. So now my eventual goal is to connect the cause to the effect, that is F1 to U1. But if I try to do that directly, it's a little more complex. So I go in steps. How can I relate F1 to sigma 11 first? Similarly, how do I relate, let's say, sigma 11 to gamma 11 using the constitutive law? Let's say the Young's modulus comes into picture. Then I relate the gamma 11 to U1, say derivative of U1 with respect to X1. Simple example of a linear strain. So even though we would have geometric nonlinearity in most problems because of large deformations that are typically involved in flight vehicle structures, because they are thin wall structures, or typically whether it's a plate or if it's a beam, it's typically thin walled. If it's a plate, it's a thin plate or a thin shell. So in all those cases, the deformation will be large, and therefore many a times you may not be giving accurate results if you use linear kinematics. So geometric nonlinearity is almost a must in all the problems. And depending upon how severely the material is stressed, the material nonlinearity will come through this particular column. But what we are more interested in eventually is always in relating this cause to the effect. And the equilibrium equations, once again, depending upon whether you have conservative loads, non-conservative loads, etc., and whether the loading is changing with the geometry. For example, if you have a rocket motor, it's a thrust that you're talking about, it's tangential to the rocket nozzle. So as the, let's say you have thrust vectoring and the nozzle deflects, you are deflecting the load that is coming over there. So you should be aware of certain things which the equilibrium equations may not necessarily be only associated with the natural laws. There can be certain thing coming because of how the deformation is taking place, and therefore the load magnitude and or direction can change based on the deformation or deflection that is happening. So those are all a little more involved things which you should be aware of, but overall it is this structure that we have over here. So let's we have a few minutes to summarize whatever we have written on the board over there. Let me start with it. We started with trying to identify those 4 types of quantities, important quantities, which are used to describe the mechanical state of stress, and we identified them to be loads, stresses, strains, and deformation. And we said that there's a direct connection between each of them in a sequential manner. Load to stresses first, and then from stresses to strains, and then finally from strains to deformation. Though our eventual goal is to relate the load to the deformation, the introduction of these 2 relatively abstract quantities helps us simplify this overall process of relating the cause to the effect. So what those 3 double arrows double-sided arrows is the green arrow is your equilibrium equations, the red arrow is your constitutive law, and the yellow arrow is the kinematics that is associated with it. And we also generalized based on certain inputs that we got just to talk about certain things which are associated not only with derivatives with respect to space, but derivatives with respect to time as well. And I think I hinted upon in another earlier class where I said that there's certain very beautiful analogies which happen in how things change with respect to space, how things change with respect to time, how a strain behaves, for example, and how a velocity behaves, for example. And you will see the structure of those equations when we eventually go and finally give the final results. You will see how beautifully they are aligned with each other. And in fact, in the Indian tradition, we call both space and time as kala. Many people think of kala as only time, but kala is also a word which is very commonly used in the Vedic texts, for example, to describe the space as well. So we had this understanding of space and time both being independent variables, and the behavior of how things change with respect to space and time. There is a 1:1 correlation that is happening, and that you can observe in the final form of the kinematic equations, as well as some of the other equations that we will talk about once the dimensional reduction takes place. Now, the first and the last of these two equations are supplemented by not only the internal behavior, but also the behavior at the boundary with the environment. In which the structure or structural component could be. So equilibrium equations has to be, along with it, you need to consider the natural boundary conditions, because typically these are differential equations, and you end up with a boundary value problem when you introduce certain conditions which are associated with it. Similarly, here also the kinematics will have certain geometric boundary conditions, because here also you're typically talking of the differentiation of the deformation with respect to space and time. So there will be certain geometric conditions which would be not only the displacement and the slopes, but also it could be the velocities. Let's say initial velocity that is given to you of a certain locations or certain material points, and how with that you're able to determine the velocity as a time history for not only those points but for all the points within the structure by using these two both in conjunction. The kinematics always go with the geometric boundary conditions, the equilibrium equations go with the natural boundary conditions. But eventually, because we are only interested in the cause-effect relationship, all of these will get combined and you'll be solving a coupled set of equations which are associated with it, especially when you go to dimensionally reduced problems. You will see simple examples of that even in 3D, but more so when you go to 1D or 2D, that is either beam theory or shell theory, you would see that all of these get mixed up in certain way, and you will have to solve them simultaneously. But so then what is the advantage of bringing up these 4 sets of variables, 3 sets of equations, etc. Even there, we are actually proceeding in this step by step and then seeing how they are connected to each other and solving the coupled system of equations simultaneously. So the setting up of the problem, how you set up the problem, how first of all you come up with the model, and then for that model you come up with the mathematics involved in terms of the governing equations, the boundary conditions, etc. All of these can be done in these stepwise sequence even before we go for the integrations with respect to either the unit normal for the plates and shells, or with respect to the cross sections for the beams, shafts, frames, truss elements, or the rods, etc., or columns, etc., all of which we are generalizing together as 1D structures or beams, or which we call as beams. So next important inference, I wouldn't call it a conclusion rather, is inference that we observed over there is not only in terms of this separation of variables, the separation of the different governing equations and the boundary conditions, but also what are the quantities that it depends upon. At least at the 3D, there's a pure dependence that is there, and which kind of gets combined when you go to the 2D or 1D models. So as far as the equilibrium equations and natural boundary conditions are concerned, they're purely based on conservation laws, in particular the law of conservation of translation and angular momentum. The constitutive law is predominantly dependent upon the material. The kinematics and geometric boundary conditions are dependent upon the geometry. So one is the set of variables, the set of equations and the supporting equations with it, and then all of them depending on certain parameters. And so that once you're aware of this, by changing certain things, you know if the change is associated purely with the material, only bother about that, keep the rest of the model as it is. So you don't need to rework the model all the way from the bottom up. When you change only the material, for example, you only change that and then bring everything together. So it's like plug and play. So you have a modular structure for this. You take out one module and put another module depending upon what you're changing. If you're changing the material, change the constitutive law. If you're changing the geometry, change the kinematics and geometric boundary conditions associated with it. But as I said, there can also be in the dimensionally reduced problems, because of the kind of entities we're dealing with, loads especially as forces, moments, etc. There can be a certain impact of the geometry over there as well. So what many of the conclusions that we are making here are purely valid for the 3D model, not for the dimensionally reduced models. Next, amongst these three sets of relationships, because we have to some extent focused on composites in this course, we're talking about the constitutive law is the only difference between your conventional materials which were used about 100 years back to what have been used in the last 40-50 years, namely the composites which are being used in a more volumes and also weight percentages in many of the aerospace applications. The only thing you need to be worried about the constitutive law. And why does the constitutive law change? There are many reasons for it, but there are two main reasons, and we have talked about it earlier as well, but to state it formally, it's essentially your anisotropy and non-homogeneity or heterogeneity that you have. And there are also ways that you can handle these. So the main reason why a composite is different from the conventional materials is that you have a non-homogeneous material, and to take care of that, you typically define volume averages, and you have to identify the typical minimum volume size that you want, what we call as the representative volume element, which could be different for different kinds of microstructures that you have. And then you are talking about volume average quantities like stresses and strains. For example, the stress is actually a quantity at a particular point, right? Strain is also a quantity at a particular point. But when you're talking about fictitious materials, which are the equivalent homogeneous materials, instead of the actual composite, then we are ending up with what we are actually doing is eventually we would it would seem that you're taking the fiber properties and the matrix properties and using, let's say, a rule of mixtures and many other things that you have looked at as part of the assignments also and in the classes as well. But why is all of that happening? It's essentially because of a volume average of a stress of that RE and a volume average of the strain of that RE, which contain both the fiber and the matrix, and therefore the actual stresses in the fibers, the actual stresses in the matrix, the actual stresses in the interface, and similarly the strains also in all three of them, were contributing towards understanding how they are related to each other, and therefore the material properties of the fiber, the matrix, all came into picture in terms of determining these equivalent homogeneous properties. So that's how we took care of the non-homogeneity. As far as the anisotropy is concerned, all that we did is, instead of Young's modulus E, we put up a subscript ij over there. Similarly, we put up the subscripts for the Poisson's ratio, subscripts for the shear modulus, etc., many other quantities, and that's how we handled the anisotropy, because by its very nature, it's a change in property from one point to another point, change in property at a given point in different directions. So at a given direction, from point to point, there is a change. And here, what we are having is at a point, direction to direction, the properties are changing. So there are ways to handle both of these, and we have already done that. Properties vary from point to point, which is what we call as heterogeneity. Properties varying from direction to direction is what we call as anisotropy. And how did we resolve these two? One case by introducing the volume average stresses and strains, which we related, and therefore the rule of mixtures came into place. So it didn't directly appear when we put up the rule of mixtures the way we calculated using the balance laws, the free body diagrams that we wrote for the fiber and the matrix as a combination or as a model with springs either in series or in parallel, etc. But essentially this is what we are looking at as a combined system, because when we are talking of two springs in parallel, you are replacing those two springs in parallel by a single spring whose spring constant is what we were trying to determine. Similarly for the parallel as well. So that is essentially what we are looking at in a discrete volume of two springs, but what we were doing is essentially in a continuous way, because these two are two continuous materials, the fiber and the matrix, which are coming together at an interface. Next, how we determine this is, as I said, by introducing your subscripts ij, which are taking care of the direction dependency of the different moduli and other properties associated with it, like the Poisson's ratio. So I think this kind of summarizes what we tried to do on the board through that particular exercise. Now we will superimpose upon this the simple problems that we have talked about in the next class, where we will first take up a rod, then we will take up a beam, then we will take up let's say a shaft, and then we'll also look at certain aspects without the actual derivation for a plate or a shell, and we will see how they start off in this fashion and how they tend to accumulate or conglomerate some of the information, especially from the material and the geometry. So once we have those three examples based on what you already know, then we will go into the more advanced theories, and we will see that they're all in the same framework. First of all, we will combine those three models, namely the rod model, the beam model, and the shaft model, into a single model where we can put all of these elements that we talked about, namely for the rod EA, for the beam EI, and for the shaft GJ. We will put these on the diagonal of a matrix and then start relating and populating, and then we will see there can be possibility of coupling between these, and how do we take care of those couplings, both from a material point of view as well as the geometry point of view. We will try to arrive at that. So this building block, one is the framework, the other is the simple examples that we start with, which you're already very familiar with and you know all it in and out. So by putting those and then generalizing it to a situation where all of these are happening simultaneously, you will see that what otherwise would look a very, very complex theory or a very complex set of equations actually follows the same kind of a paradigm. Thank you.